All right, welcome back, everybody. It's time for another cool math proof. So it turns out there's infinitely many prime numbers. And remember, prime numbers were the natural numbers that were larger than 1, that were only divisible by 1 and themselves. So like 2, 3, 5, 7, 11, 13, 17, etc. Well, it turns out there's infinitely many of them. We're going to prove that right now. So we're going to do an indirect proof. We're going to do a proof by contradiction. And so the idea is we're going to assume the opposite of the statement, follow good logic from there, and we're going to arrive at a contradiction. Well, if we followed good logic, the fault is in my assumption. So the opposite of what I assume will be true. So let's assume the opposite and then again follow good logic after there. So yeah, let's assume there's finitely many prime numbers. And let's assume we could list them all in order. So yeah, then we're able to list them all in order. So we've got P1, which will be the smallest prime, so P1 would be 2. And then P2 would be 3, etc. And so we have this list. Okay, so with the property that P1 is strictly less than P2, which is strictly less than P3, which is strictly less all the way down. And so we're assuming that the largest prime number is P sub n. So from here, we're going to consider and construct a new number. So this is just some number. So I'm going to say consider the number. Let's call it A. And let's say A is the product of all of these prime numbers, then plus 1. So we're going to take the product of this entire list of primes, this finite list we're claiming, and then we're going to add 1. Okay, well, A is clearly larger than 1. So let's note that. So I'm going to say since A is larger than 1, well, by the fundamental theorem of arithmetic, A has at least one prime divisor. So the fundamental theorem of arithmetic says that every number that's larger than 1 can be expressed as the product of primes or itself is prime, and it does that uniquely. So for example, 2 is prime, 3 is prime, 4 is 2 times 2, prime times prime. 5 is prime, 6 is 3 times 2, prime times prime. Okay, so the point is A has at least one prime divisor. So let's call that prime divisor P sub k. So we're going to assume that this is some P sub k. And so P sub k divides A for some k. And since we've claimed we've listed all the primes, that k must be between 1 and n. Okay, well, now we have a statement about divisibility. Remember how to read this. It says P sub k divides A. So now we want to invoke the definition of divisibility. So by the definition of divisibility, there exists some integer j such that, well, what does it mean that P sub k divides A? It means that P sub k times j equals A. Right? That's exactly what it means for this to divide A. Well, it looks like we can make a substitution, right? Because, well, we have A is equal to this, and A is also equal to this, so therefore I can replace this A with exactly this, and that's what we want to do next. So we want to rewrite this statement here with A replaced with P sub k times J. And so by substitution, P sub k times J is equal to the product of all the primes, which again, we're claiming there's finitely many, plus 1. So yeah, again, that replaced A in that statement from before. But in particular, we want to make an observation. So k, we said, was some number between here. So that means I can really think about this in a particular way. And you'll see in a moment why I want to think about this in some way. So I could say that this could really be thought of in this way. So I could say P sub kj is equal to P1 times P2 times P3. And maybe somewhere in between, I finally get to P sub k minus 1, P sub k plus 1. Continue in this way, and then I finally arrive at P sub n, and that's plus 1. So that's just making note that that's in there somewhere, right? Because that's one of the primes that's in our list. And so the idea now is we want to divide both sides by P sub k. Notice that'll cancel out that P sub k. That'll cancel out that P sub k. And because these are two terms, I'll have 1 over P sub k. So dividing both sides by P sub k yields the following. So J is equal to P1 times P2 times P3. Again, keep in mind this was canceled out because we divided both sides by P sub k. So I've got P sub k minus 1, P sub k plus 1. Again, that was divided out. P sub n plus 1 over P sub k. Again, because when you divide, of course, both terms, this term and this term. Okay, so let's sort of observe something. So we know that j is an integer. This is the product of a bunch of natural numbers, so that's an integer. And so let's bring the integers to the same side. And so we have j minus P1 times P2 times P3, Pk minus 1, Pk plus 1, all the way down to Pn is equal to 1 over P sub k. But that should baffle you because this is the difference of integers, so this is clearly an integer. But remember, P sub k was a prime number, and 1 over, or the reciprocal of a prime number, is never an integer. And so this is a contradiction. I can't have an integer equal a non-integer. So what does that mean? Well, if I assume something and follow good, strong logic afterwards, and I arrive at a contradiction, the fault wasn't in my logic, the fault was in my assumption. So therefore, the opposite of what we assumed is true. So therefore, there are infinitely many prime numbers. I love that proof. Such a classic.